Alright, in this video we show that the sum of two Gaussian random vectors is again a Gaussian random vector. Specifically, if x follows this Gaussian distribution with the mean of mu x and the covariance of sigma x, and y is another Gaussian random vector that follows Gaussian distribution with the mean of mu y and the covariance of sigma y. Then their sum, x plus y, follows a Gaussian distribution with the mean of mu x plus mu y and the covariance matrix of sigma x plus sigma y. In a previous video, we proved this fact for univariate Gaussian distribution. And the way we prove this for multivariate Gaussian distribution is quite similar to the univariate case, but it becomes a little bit more complicated because we have to deal with vectors and matrices. Anyway, let's start. Before proving this main result, we need to prove a little lemma first. So let's do that first. Okay, lemma. And suppose A and B are invertible matrices, so they are regular matrices. And also assume A plus B is invertible. Then we have the following identity. A plus B inverse is equal to A inverse minus A plus A B inverse A inverse. And of course, by symmetry, this is also equal to B inverse minus B plus B A inverse B inverse. Okay, let's prove this. Suppose we have this. A plus B inverse is equal to A inverse plus X. And we show that this X should be equal to this part. Then we have A plus B inverse times A plus B is equal to A inverse plus X, because this is replaced with this, A plus B. And this is equal to, this times this is identity matrix, and A inverse B plus X, A plus B. But this left-hand side is equal to the identity matrix. So I is equal to I plus A inverse B plus X times A plus B. So therefore, X A plus B is equal to A inverse B. It's negative here. And we are, of course, assuming that A plus B is invertible. So X is equal to negative A inverse B A plus B inverse. And we have inverse here and B here and inverse here. And let's take the inverse of everything. Then we swap the order. A plus B, B inverse, A, everything inverse. And now let's expand this inside. Then A, B inverse, A, and B times B inverse is identity, and this is A inverse. So let's rearrange this a little bit. And here. So therefore, after all, A plus B inverse, so this is X, so our original assumption is this, so A inverse minus A B inverse, A inverse. And of course, similarly, if we just swap A and B, and by symmetry, we have B inverse and B A inverse, B inverse, and we are done. Okay, now we are ready to prove our main result. Let's assume these vectors are n-dimensional vectors, okay, n-dimensional. Okay, so let's first define a random variable z that is x plus y. By the way, we are assuming x and y are independent of each other. And we want to find the density function of z. And that is calculated as the product of the density functions for x and y. X, and this is normal distribution, sigma x, and the density function of y. But let's say y is z minus x. So we fix the value of z and move the value of x, and the value of y is determined by this. So it's z minus x, given the mean mu y and the covariance of sigma y. And we integrate with respect to x for entire space, n-dimensional space. And since both of these are normal distributions, and we have the following. Integrate, and from here we have 1 over square root of 2 pi to the power of n and the determinant of sigma x, and 1 over square root of 2 pi to the power of n and the determinant of y, and times exponential. From this one we have x minus mu x transpose sigma x inverse x minus mu x over 2, and 1 over 2, and z minus x transpose sigma y inverse z. Wait a minute. Don't forget the mean mu y here, and sigma y inverse z minus x minus mu y, and dx. And right now we want to integrate this function, okay? And this part is constant, and inside this exponential, this is actually a quadratic form in x. So first thing we want to do here is to complete the square with respect to x. So that's what we do. To simplify things a little bit, let's define z prime as z minus mu y. Okay. Then consider this exponent part, and that is x minus mu x transpose sigma x inverse x minus mu x plus z prime minus x transpose sigma y inverse z prime minus x. From now on, it's just a brute force calculation. So I just shut up and do the calculation, okay? X sigma x, x transpose, and x transpose sigma x inverse mu x, and this is negative, and mu x transpose x plus mu x transpose sigma x inverse mu x, and z prime y inverse z prime minus x transpose z prime minus z prime transpose and x plus X transpose and X. Okay, so we have X square here, and X here, X transpose here, and X transpose here, and X and X. Okay, so X transpose sigma X inverse plus sigma Y inverse X and X transpose sigma X inverse mu X and this one and sigma Y inverse Z prime and minus mu X transpose sigma X inverse and Z prime transpose sigma Y inverse X. And the remaining terms, that is mu X transpose sigma X inverse mu X plus this one, Z prime transpose sigma Y inverse Z prime. Now, notice that this vector is the transpose of this vector. Okay. Oh, wait a minute. I think this is wrong. So this is sigma Y inverse here. Okay. And let's define a new vector B as, so we want to have here this matrix in here and here. Okay, so to do that, we define B as sigma X inverse sigma Y inverse of sigma X inverse mu X, so this vector, sigma Y inverse Z prime. So if we put this way, then this is equal to X transpose sigma X inverse sigma Y inverse X minus X transpose, and we have this matrix here, sigma X inverse and sigma Y inverse B. And we have B transpose sigma X inverse sigma Y inverse and X. By the way, sigma X and sigma Y, they are variance covariance matrices, so they are symmetric. Therefore, their inverses are also symmetric, and therefore their sum is also symmetric. So this is a symmetric matrix. So therefore we can, omit this transpose sign here. So we can just write like this, and the rest, mu X, and Z prime, and Z prime. Now we can almost complete the square. This is equal. And let's write it here. So X minus B transpose sigma X inverse plus sigma Y inverse and X minus B, and minus B transpose sigma X inverse sigma Y inverse B, and the rest. And for simplicity, let's put all of these extra terms as E. So if we put this back to the exponential function, and we want to integrate this exponential negative 1 over 2, this thing, okay, x minus b transpose sigma x inverse sigma y inverse and x minus b plus e dx. So if we integrate this, we have, so this part is constant, so let's leave it alone. And times square root of 2 pi to the power of n times the determinant of the inverse of this. Okay, but the determinant of an inverse is the inverse of the determinant, so that is square root of 2 pi to the power of n, and the determinant of sigma x inverse plus sigma y inverse. That's it. Now let's put this back to the original integral. Then we have rho z as, what was it? 1 over 2 pi to the power of n sigma x here, and 2 pi to the power of n sigma y here. And now we have this 2 pi to the power of n and determinant of sigma x inverse plus sigma y inverse times exponential of negative e over 2. So this cancels this, and we have this times this times this. And as you know, the product of determinant is the determinant of the products. So this thing, sigma x times a determinant of sigma x times determinant of sigma x inverse plus sigma y inverse times the determinant of sigma y. This becomes the determinant of sigma x inverse plus sigma y inverse times sigma y. So just multiply everything and we have, let's see, so this times this is identity, and that times sigma y is sigma y here. This times this times this, that's sigma x. So after all, let's put this back to here, and we have rho z is 1 over square root of 2 pi to the power of n times the determinant of sigma x plus sigma y and exponential of negative e over 2. So what was this e thing here? That's this. Okay, let's tidy this up. So this e thing is this. E is z prime transpose sigma y inverse z prime and minus b transpose sigma x inverse plus sigma y inverse and b and plus mu x sigma x inverse mu x. Well, this is again a very tedious calculation, but let's consider this term first. First of all, what was b? So the vector b was defined as sigma x inverse plus sigma y inverse times sigma x inverse mu x plus sigma y inverse z prime. And let's put this into here. So we have b transpose sigma x inverse plus sigma y inverse b. This is equal to, so take the transpose of this. We have mu x sigma y z prime transpose, and transpose of this thing is just this thing because it's symmetric, and we multiply this with this, so they will cancel, and we are left with one of this inverse. So that's sigma x inverse sigma y inverse inverse times this part, sigma x inverse mu x sigma y inverse z prime. Now let's expand this all. This times this, mu x sigma x inverse sigma x inverse sigma y inverse inverse, and times this, sigma x inverse mu x. Okay, and mu x transpose sigma x inverse sigma x inverse sigma y inverse inverse sigma y inverse z prime, and z prime transpose sigma y inverse and sigma x inverse mu x, and z prime transpose okay, now let's consider this part. Okay, so we have sigma x inverse plus sigma y inverse inverse and sigma x inverse. Okay, this is equal to sigma x times sigma x inverse plus sigma y inverse times sigma x, everything inverse. And this is equal to, so this is sigma x, this times this times this is sigma x, and this times this is sigma x sigma y inverse sigma x, everything inverse. And next consider, let's see, this part. So that is sigma x inverse plus sigma y inverse sigma y inverse, and this is equal to sigma y inverse, wait a minute, not inverse, sigma y sigma x inverse plus sigma y inverse times sigma x, everything inverse. Okay, so this is equal to, this times this is sigma y, and this times this is sigma x inverse. And now what? This one is the same as the previous one. So this one and this one, they are the same. Now consider this part. So sigma y inverse here. Okay. So by symmetry, sigma y inverse sigma x inverse plus sigma y inverse sigma y inverse is equal to, that should be sigma y plus sigma y sigma x inverse sigma y, everything inverse. All right, now put this all into E. So E was, let's see, let's go all the way to here. So we have this, and we just found this and add this. Okay. So Z prime transpose sigma y inverse and z prime minus b transpose, what was it, sigma x inverse sigma y inverse b plus mu x transpose sigma x inverse sigma mu x. So this is equal to, for this part we have this. So let's see. Let's consider z prime part here. So for this one, we have z prime transpose z, and z prime transpose, we have sigma y inverse, and we have this, and don't forget the negative sign here. Then we have sigma y and sigma y, sigma x inverse, sigma y, everything inverse here, and z prime. And then consider the part with z transpose, z prime transpose. So that is this term. Okay. And this matrix part became, what was it? Just sigma x plus sigma y inverse. So the next term is minus z prime transpose and zx plus zy inverse and mu x. And next, consider the term containing mu x transpose, this part. Okay, similarly, this matrix became sigma x plus sigma y inverse, so we have minus mu x transpose sigma x plus sigma y inverse z prime. And finally, consider the term that is quadratic in mu x. So that is this term, and also, where is it? This term. Okay, and the matrix part here became, where is it? This one. So, plus mu x transpose sigma x inverse minus sigma x plus sigma x sigma y inverse sigma x inverse and mu x. Now we use the lemma we proved before. This matrix is equal to the inverse of sigma x plus sigma y, and this matrix is equal to the inverse of sigma x plus sigma y. So after all, we have the same matrix here, 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 here. So therefore, this can be factorized as this: z prime minus mu x transpose sigma x plus sigma y inverse z prime minus mu x. So let's put z prime into the original form, that is z minus mu y. So we have mu x plus mu y here. Transpose sigma x plus sigma y inverse and z minus mu x plus mu y. So after all, the density function of the random vector z is given as 1 over square root of 2 pi to the power of n, and the determinant of sigma x plus sigma y times exponential of negative e over 2, where e is this. So that means the normal distribution with the mean of mu x plus mu y and the variance covariance matrix of sigma x plus sigma y. And we are done. Alright, that's all for this video. See you next time. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.